Hello everyone. Um, I hope you can hear me. And yeah, it's a funny actually stream because um, I have already done one, and then I have realized in the end of that session that there was no sound. So it's a bit annoying, but yeah, it's also maybe good for me to be more attentive next time. So, so for those who have not attended the previous one, um, I'm checking. Do you can you hear me now, guys? Actually, let me know because seems like. Uh, Sorry, one moment. Here's the moment when technology fails me. Actually, yeah, I can hear it, so it means that you also have it. All right, so perfect. Let's start once again. So today we're going to try to model, not try to model, but actually model this geometry, which is an exoskeleton, which has been developed by using Grasshopper 3D and some plugins such as Heteropter, Weaverbird, and some other tools. So it looks really, really complicated and convoluted, this pattern, and that's what I guess at least that's what I like about it. But in fact, if we start looking at the way it's done and at the details it's made of, we realize that it's just like a series of rhombotruncated cube octahedrons, which again, it's I say it's like simple, but it's not. It's quite a tricky shape actually. But today I'm gonna show you how to make it, and then we're going to make this pretty lattice from a series of these shapes. So what is a rhombotruncated cube octahedron? Basically, it's a cube which is trimmed in like several ways, and then we get this geometry. So I'm gonna just start building it, and then you will see that it's actually not as hard. It's quite simple actually. So let's start with constructing a point, and let's then go for polygon. In our case, we're gonna use an octagon, so it's gonna be like our base, let's say. So yeah, for the actually let's switch to shaded mode. Yeah, you see basically this is the octagon, and this is the radius will be set to 10, for example. I want to make it a bit bigger, yeah, something like that. Then I'm going to rotate it a little bit because I don't want it to be like that. I don't want it to stand on the point. Um, um, and yeah, sorry, one second. Okay, so yeah, let me know, guys, if you can hear me because I get some comments that there are some issues with sound as well. Sorry, one second. Yeah, right. Yeah, I can hear myself. It means that we have the sound. Perfect. So yes, let's get back to the script. This octagon, I don't want it to stand on this point. I want it to actually stand on this base. So I want it to be rotated by I don't know, yeah, some angle, and this angle will be defined by the number of corners, which is like 8. So we're going to divide 360 by 8, and then I'm going to divide it by 2 because it's half of the corner, half of the angle as well. Going to say it at 2 degrees, and now we have this geometry rotated. Perfect. Then we need to start placing the squares, right? The squares are adjacent to the octagon, and if you look at this one, for example, we have the octagon and 4 squares attached to it, yeah? So something like that. Let's explode the octagon. Let's dispatch the lines. Like I'm gonna pick the ones, sorry, not this one, but the other one. I want to pick these ones, yeah. And then I have to move I have to make these squares. So in order to do it, we need to take the center of each of these lines. We need to take the general center, yeah, for all of them. And then we build a vector between two of these centers, like this. And we move our curves following these centers. So we do something like this, yeah. And then we get, is it actually, no, actually it should be not like that, because this is like a bit too much. So we should use amplitude of this, so we should use vector from this vector and the amplitude defined by the length of these lines, because after all we're using it to make the cube, sorry, not the cube but square, which means that all the edges should have the same length, right? So we basically do it like that. Then we go for a ruled surface. This is 1, this is 2. Done, yeah? This is quite straightforward. Now we have to rotate each of these squares by 45 degrees in order to get this kind of, because it cannot be flat, it has to have some volume, right? So we have to rotate it, and we have to rotate it by 45 degrees. So seems pretty straightforward and pretty simple. So we take these centers and we take the, let's say, curve closest point. For each of those curves, I'm taking one center, like that. Taking this curve, then we need to take the perp frame, because now we're going to create the frames for rotation, yeah? So something like this. And then, yeah, then we just say rotate, and we rotate these surfaces in these planes by 45 degrees precisely, yeah? This. The only thing I don't like is that I want these squares to be rotated upwards, not downwards. Therefore, I would like to say set this rotation to negative. Yeah. Now I like how it looks like. Perfect. So after that, we should start actually making these octagons on these edges. Yeah. So the easiest way to do it, well, not the easiest, but probably the most straightforward way, will be to just take this octagon and orient it based on these curves. So how should we do this? Well, also quite simple. First of all, I take the brep edges. I have to find a center for each of them and deconstruct it. And then we just can sort our list to find the highest point. Yeah, so like in our case, it's gonna be the last element in this list. So we have to go for -1, which is like last element. Yeah, like that. Done, you see? And now what we need to do, we need to create the planes to orient this octagon into these planes. So how are we going to do this? Again, pretty straightforward. We take the center of those curves, we take the line SDL, which is start, direction, and length. The direction is set to Z, so basically it's going vertically up. And the length is, it doesn't matter for us, because we just need this curve to define our new planes for orientation. So I go to vector, plane, line plus line. And then this line will be y. And now we need to make the x line, like the main line of this plane. And it should be like half of this curve. So let's take the subcurve. It's a component which is I see it used quite rarely, but it's actually quite a useful one. So I'm just going to show you how it works. Basically, you can take a domain on a curve and pick any domain from it. I would say from 0.5 to 1, maybe, something like this. Should be fine, I guess. And this is our planes. These are our planes, yeah? So like that. Then I want to pick the same plane for our original, sorry, I'm gonna hide it. For our original octagon, and let's say I want to pick one of those centers, like that maybe. Yeah, one of these. I'm gonna set XY plane to the center, and also I'm gonna take that curve, like the rotated one. Yeah, something like this. So now, when we use the orient component, we take the curve, we take the base plane, and we take the last plane. You see, right? The only thing which is not right is that these octagons, they are now looking down. So the way we can solve it is actually by just setting up this thing to -x, and there we go. Yeah, pretty straightforward, right? Okay, so I keep deleting it, but I should not. I should take actually these B-reps like that. Yeah, so then I will also create boundary surfaces from these octagons because they are closed, they are planar. So why don't we make a just really nice closed boundary surface from them? All right, so this is done, and then it's time to mirror those geometries, yeah, like these ones, and also the original one, which I think I can also turn into a boundary surface because it's also closed and flat, planar. So we get this set of geometry, and then another step that we should do is first of all, we should flatten it. I mean, I know that I keep telling my students and I keep telling you guys that we should never flatten, but in this case, we don't really care because we're making one particular geometry, and yeah, we don't really care about the data structure that much. Yeah, so we take one center for all of them, and we use it as a base for the XY plane to mirror those elements. So we say merge, we say mirror, and we mirror them using this as a mirror plane. And this is our geometry. Yeah, almost there, guys. Almost there. Almost done. So now we should merge our no, before merging, actually, we should start building those squares on the edges. How can we do this? Well, I would say the fastest way will be to take the B-rep edges from our octagons, taking the centers for not centers, but actually have a better idea. We can just take the edges from directions, because those are B-reps, right? And B-reps edges, they have direction, and we should pick Z-axis as the direction. And you see it automatically picks those edges. We can even set some angle tolerance, yeah, for like, let's say, of around 1.5 degrees, maybe more or less. Yeah, and then we take those edges, and now we need to group them by pairs. Like, we need to pick the closest ones. So how can we do this? Well, let's first of all take the centers of those edges, and let's take the point groups. I'm gonna flatten this as well. Yeah. What is the point groups? The point groups is a component which creates groups of points based on their proximity to each other. So if you provide a distance which defines the proximity between points, for example, my goal now is to make sure that these pairs of closest edges, they are grouped together. And this distance can be actually defined as well as the length of the side of the square. So I'm just going to take the one of those lengths because I don't need all of them. They are all the same. Yeah. I'm going to take this length as a number, and I'm going to multiply this number to make it a bit tiny, just a tiny bit bigger than how do you call it? Then then the side of the square. So I'm gonna make it 1.01, really tiny difference, and I'm gonna use it as a distance. So now, as you can see, we get 4 groups of 2 edges, right? So they are grouped by proximity. I'm going to use this as the index and this as the list. And after that, what I want to do, I want to loft them. You see, it worked, but this loft gets self-intersecting because these curves, they go in different directions. So what is important now is to flip one of those curves. Yeah, so that they all go in the same direction. And then after that, we don't have to bother ourselves by grouping them again and merging them again and lofting them again. We just can do the ruled surface, which is also going to be planar, by the way. And now it's time for us to merge everything together. So we take our mirror geometry, we take our original geometry, we take our octagons, and we take our extra squares. So something like this, yeah? We hide all the rest, and we flatten everything here. And after that, I say brep join, which means like we make single joint brep. And we don't have to bother ourselves by making these hexagons. We can just cap holes instead, right? So like this is it. This is our geometry. All right, guys. So yeah, I'm gonna save the document maybe later on. But I actually suggest to everyone who is repeating after me to save the document, because this way, when you have a file saved, your Grasshopper, if it crashes, it will automatically save your file, and will let you open it. Actually, let me just do this. Yeah, here. All right, so now we need to start building our array of these boxes. So let's make the box array. I'm going to use this as a geometry, and then I want to use the bounding box as a cell as a unit for my box array. Why? Well, because apparently this rhombotruncated cube octahedron is a derivative of a cube. So it's really similar to the cube by its shape, and it's almost like a trimmed. I mean, it speaks pretty much for itself. It's a trimmed cube. So I'm going to create 3 sliders. This one I'm going to set to 3 for y, and z and x will be set to 5. So I get something like that as a result. And basically this is it. Like, this is our initial geometry. But what is important now is that we start making our lattice to create this kind of exoskeleton here. So in order to create a lattice, we take the brep wireframe. Yeah, it already looks quite nice to me actually, but this is not it, of course, guys. So yeah, we get this geometry, then we need to flatten it again. I mean, alternatively, I also try to develop this habit for quite a long time to use shift paths instead of flatten. Even whenever you need to have a flat tree, it's still better to use shift paths, because maybe, quite unlikely, but maybe if you have a very powerful PC, you can use multiple arrays like that. But I have quite a modest laptop, so I will just use yeah, this component. And then it's also really important to get rid of the duplicates, because you can see sometimes our geometries are touching each other, and that's the part where the lines get duplicated. So I want to say remove duplicate lines. Yeah, and you see that the difference is quite significant. It's like 1500, almost, it's 1400 lines almost, yeah, so it's quite a lot. And then I'm gonna go to Heteropter plugin, and I'm gonna use the network component, network from lines, which basically creates, which gives me more information about the geometry, but most importantly, it gives me the lines, which is like the rods, and the nodes, which is like points, yeah. So we're actually having we're having a course about networks and meshes and subds starting in the end of February, beginning of March. So if any of you would like to learn it, guys, please feel free to text us and reserve your spot. We still have some spots left. And yeah, if you have any questions or any ideas, any suggestions about this topic, let us know. We'll be more than happy to help. We can either arrange like an individual consulting or a group, or even maybe in one of our next streams, where, like our next live sessions, we can also talk about something like that. So, having said that, let's get back to the script and let's move forward. As you can see, we get all the points and all the lines here. So the most natural thing to do now is to take the multipipe component, define the radius to something like 1.2 maybe, node size I mean, and then we just connect the lines to curves. And it takes quite a bit of time, like 1.5 seconds, 1.7 seconds. But you see we get this result. It already looks quite nice. I mean, at least for my taste. So let's quickly take some nice color by custom preview. And let's take a swatch and let's give it a nice color from the preview. I mean, at least I kind of like it. You can give it any color you want. And then if we look at it in render mode, you see that basically we get this kind of really complex and quite nice geometry, I would say. Yeah. I'm still not completely convinced with it. Like it's already quite nice, but it's too similar, too uniform. So first of all, what I would do, I would change the strut size. This is like the size of the rods, basically, like how, yeah, it gets a bit thinner and the nodes basically stay as they were. So this already looks a bit better, actually I think a lot better. And the next point I'm gonna do is actually give more variety to the radius of the nodes. So let's take the center of our network, say from here, maybe for all, yeah, one center. And let's use pull point to as an attractor point for those points here. So let's use Normalizer to basically what it does, it takes the domain of the distances and it brings them into the domain from 0 to 1. And GraphMapper works with in a domain from 0 to 1, so it's like kind of compulsory for us to do it. And then we remap numbers, we say bounds. Basically, it's like a very default operation. I've been showing it many times, even during our live sessions, and I assume pretty much everyone knows it. So then we construct our domain, and I want this domain to go from 0.8 to something like 2.1 maybe. Maybe it's a bit too much, but let's see, maybe 1.8 should be fine as well. Just saying. And let's now, also we need to provide size points, because this component needs to know which point gets which radius, right? So, and then we go for node size and we connect these different numbers into node size. And now it gets a lot heavier, but you see that now we actually start getting some, in my opinion, quite a nice result. Yeah, so it's like really nice. It's really like different, and also we can instead of this point, by the way, instead of this center point, by the way, we can use any curve, any other attractor, any parameter. So it's like really gives quite a lot of possibilities. And then I would prefer to keep it thicker in the center and thinner on the sides, so it gets a bit yeah, a bit more air on the yeah, something like this. Oh, actually kind of like it. Okay, That's nice. So yeah, basically what is missing now is just another layer of complexity, which I wanted to show you guys, which actually is not even shown here. So I'm kind of showing you more than on the preview. But what I wanted to show you is actually how can we add another lattice on top of this lattice? How can we make this, how can we add some more resolution, more texture to this thing? So first of all, we need to convert our multipipe into a mesh. So I'm gonna say mesh from sub D, or sorry, mesh from sub D. Yeah, this one. And it's a really nice component because basically Multipipe already has a really clean and really like quad topology, right? So it's we don't even need to do anything special for that. We can just make it like this, and then yeah, we can control the resolution. But I think for us, this resolution is more than enough for the moment. So let's go to Weaverbird plugin. Let's take it's a really nice plugin, by the way. If you have a chance to find it online, like I encourage everyone to install it. It's been originally made for Rhino 5 or 6, I don't remember exactly, but it's a really, really useful tool. It's still completely valid in Rhino 7. This component basically doesn't use an absolute value, it uses a relative value. So I'm gonna set it to 8.5, for example. Yeah, something to give it a bit more width and thickness. And then finally, I want to use this component, which is called Weaverbird Mesh Thicken, and this component, for some reason, I don't know why. I mean, I'm pretty sure there was a reason, but at least I'm not aware of it. It uses the absolute value, absolute distance. So for this particular case, we need to make it really, really tiny, because otherwise our geometry is going to look too bulky and like actually it will not make sense. And right now we get quite a nice and quite a coherent grid here. And the only thing which is still missing, at least for me, is basically I want to make it a bit smoother. I want to make it a bit more like a lattice. So I will take this component called Weaverbird Kettle-Clark Subdivision, and I will just apply it here. It will take around 5 or 6 seconds to compute, but in the end we're gonna get quite a nice and organically looking shape. Yeah, it takes a bit of time to process, but yeah, you see, right? We get this kind of nice geometry. We can also do something like this before that to increase the resolution a little bit. It's gonna go like exponentially heavier, so it's gonna be really heavy. I highly don't recommend you to do this if you have not the most powerful laptop. Maybe if you, I mean, my laptop is quite good, but it's still not as powerful as a PC. So just saying, be careful with it. I'm gonna take the risk, but first I want to see how it looks like without this fancy shape. Let's say without this fancy subdivision, without the extra subdivision, let's say. And ooh, I kind of like it actually, like this. It's quite a nice color, as for my taste at least. Yeah, maybe I'm gonna make it a bit more bluish. Yeah, I don't know, something like this. Yeah, I kind of like it. Okay, so then last step I want to take is I want to make this. I'm gonna save first of all, and then let's test how good is this laptop really. Let's take this one, and basically if I made my calculations correctly, the amount of polygons is going to be 4 times as much. So I think the Catmull-Clark will take around half a minute to compute, and then maybe a bit of time to render this geometry, because rendering sometimes takes even more time than processing this geometry. So sometimes when you're working with a really like polygonal shape, it can yeah, I was almost correct. 30 seconds and 30.3 seconds. Yes, but I think the result was totally worth it. You see, like now it gets much more elegant, I would say. It's not very like it's not a circle, let's say. It's more close to a filleted rectangle, or just like quad, let's say. So I really like how it looks. I think it's quite nice, and I think we can yeah, I think we can go from there. We can develop it even a bit more. So yeah, guys, thanks everyone for watching and for joining us today. I hope it was helpful for you. Also, as mentioned before, we start new Grasshopper courses and new Grasshopper groups pretty much every other week, I think. Once per 2 weeks, we start a new batch. So feel free to contact us, follow our Instagram. Also, if you have any ideas or suggestions or questions about the content of this tutorial, please leave us a comment and yeah, let us know what you think. And then any ideas are for the upcoming streams and upcoming live sessions are more than appreciated. We're also going to make a few more sessions in the following weeks. So if you have any ideas or if you'd like to see something particularly, please let us know. And if you don't want to wait for a particular topic to be shown on YouTube, just drop us a message or comment. We will arrange some classes or consulting with you, and yeah, we can discuss it. So thanks to everyone. Have a nice week, and goodbye.